So what we have here is we were trying to emulate a butterfly flapping mechanism. We had a couple different failures in the beginning where we had to learn ourselves what the actual definition of the flight was, why it flew. This model, in the beginning, we decided couldn't work because it was just force cancellation. This model right here works very powerfully as a glider because it's got a motor, but it's too heavy to create its own lift in the beginning, so it doesn't take off by itself. We moved along and had models like this, where we have the cyclical motion of the wing, but we didn't have the power delivery system. We couldn't find a motor with enough torque to give it that flight, so we had to abandon it. And then we have models like this right here that have a moving shaft that changed the angle of attack on the wing beat. And we couldn't have enough powerful enough delivery system or accurate enough system to make this front mechanism because our 3D printer was not accurate enough to get parts of this small size. So we actually ended up settling on a front crank rubber band powered model that you can put dump potential energy into in the rubber band. We made the frame super sturdy so we can put a lot of power into it, crank it up like that, and then let it go from rest. Creates a lot of thrust out the back, but we were pretty confused as to why we couldn't feel any lift, and what we did was we wanted to see where all this lift was coming from, so we made a faux wind tunnel test with a fog machine and put a filter over it, and you can see all the air above the wing is being sucked down. So this is actually flying like how a bumblebee flies. A couple decades ago, mechanical engineers couldn't figure out why bumblebees flew. It's because they were too heavy. Laws of conventional flight mechanics wouldn't let them fly, so they were very confused. They put it into a type of test like that, and they saw that there were all these vortices and eddies being created over the wings. That creates a low pressure region, which creates suction. When you have a low pressure region on top, high pressure region on the bottom, causes a flow upward. The pressure's trying to equalize because they want to go to equilibrium. Creates a lift on the actual butterfly, which is different than a bird flying because a bird's wing is an airfoil. So as those flap, they have pressure difference because of the different amount of space top and bottom of the wing, whereas an insect on a thin membrane flaps, creates a vortice above the wing, sucks it up into the air. So we tried as best we could to emulate that. The tails are only there to stabilize the flight. The way we actually got our drop testing was we to prove that it didn't just glide, we did one without a wing flap, so it just falls. And then we did one, a low frequency flap, just falls again. And then our high frequency flap, from about 10 feet in the air, it flies about 20, maybe 22 feet outward. And then we have a more clarified no wind interference one, where you can see it drops, levels out, flies, and then once you lose the transient response to the rubber band, loses all its power and drops. And then we came into a couple problems with this, like we couldn't figure out why they kept turning around. It's actually because when we would fly it, we'd pull our hand away, create a vortice with our hand, influence the flight, the suction of the wings, and turn it around.
Okay, I was wondering, I was watching the cranking motion, I was wondering if one wing was flapping at asymmetrically.
Yes, both wings actually do flap asymmetrically, but at the frequency that we're obtaining on the high potential energy rubber band twist, it doesn't matter because it's so quick that it evens out fast enough to, the vibration doesn't really change much.
Is this an existing project that's been done before?
No, we designed this from scratch.
Do you think you accomplished what you were set out to do?
Absolutely. Our professor dictated to us, I want you to make a mechanism that you can let go. It will fly 5 feet forward. It doesn't have to maintain steady flight, but it does have to fly forward, and it can't just glide. So we had a couple models that did just glide. We had to scrap them, completely redesign the project. Now we have a model that, as you saw, does not fly if it's not flapping. That forward motion and lift is completely reliant on the flapping and nothing else.
How do you think the managing of the project? I mean, how did that go? Splitting up teams, whatever.
We divvied up the responsibilities after the research. We did the research as a group, determined everything together, and we worked together we sat around a round table and planned out and listened to everybody's ideas. We were going to go with the Dragonfly at first, and we decided we didn't want to do that because there were too many process mechanical parts that would take too long. We have very little room for error. So we did a simple balsa models like this, and when one didn't work, we sat down as a group and we discussed better options and changed it, and we did everything as a collective. There wasn't really a clear leader in the project. We all had equal say and equal portion. We all worked together as a team and got the project done.
How'd you divide up who's going to do what?
Sure.
Okay, time's up, guys.
All right, you very much.
Thank you.
Well, thank you very much. Yes, very nice.